All right, it's 11:01, so let's go ahead and get started. Good morning, everyone. During the webinar, if you have any questions whatsoever, please feel free to drop us a chat. We're going to be monitoring. Actually, we've got a Q&A as well, so if you have any questions whatsoever, we're going to be monitoring that. We're going to try to get those to you as quickly as possible. If we don't get to it during the webinar, then we'll definitely reach out to you with any of the questions that you have. So. This morning, we're going to be covering mesh-based FEA versus Altair SimSolid. Robert Smith is our solution consultant. He's the technical person that knows it very well, and he's going to be demonstrating much of Altair SimSolid. And my name is Edmund McClure. I'm a sales rep with Team D3, and I also work directly with Altair. We'll be talking a little bit more about that at the end of this webinar. So, Robert, it's all yours.
All right, thanks, Edmund. A pretty simple agenda today. Just to let you know where I'm going to be taking you today. I'm going to briefly introduce SimSolid, what it is and why it's different. We'll take a look at the workflow of SimSolid versus the workflow of a traditional mesh-based tool, and we'll get into a little bit of why it's such an advantage that SimSolid does not need a mesh, because the meshing is difficult, right? So we'll talk about some of that stuff, and then I'll get into a live demonstration of SimSolid itself. So this is some of the key stuff that I want to drive home with what I'm talking about today. Why SimSolid is different. It is a structural analysis tool, but unlike what you'd be used to if you've been using FEA tools for any length of time, we're going to be using the original CAD assemblies unsimplified, without all the upfront work that you're typically used to, because it doesn't require a traditional finite element mesh. So if you do have experience in these tools, you'll understand right away what a big deal that is, what it means to have to prep CAD geometry and mesh. If not, I'll be talking about that a little bit too, the kinds of difficulties and time-consuming processes that are involved in traditional finite element meshing tools. So SimSolid is different in that we could skip all that, and we can get to results much quicker in seconds or minutes, whereas you might typically spend hours up front even getting to the point where you can run an analysis. So that's really the main point of today. I want to drive that point home and show you what it looks like in the product itself. So when we're talking about a structural analysis tool, an FEA tool, whatever you want to call it, that uses a traditional mesh, the workflow looks something like this, right? Where we start with a CAD model. That's very common today. There are tools out there that allow you to build meshes directly without CAD models, and that's still appropriate sometimes. But most of the time today, we're starting with a CAD model because we already have it. We need it anyway to define the design, to plan the design, to document, and actually produce our product. So why not take advantage of that for FEA? That's very common. But there is a lot of work getting it from the point where we have a model that's good enough for documentation to a model that is appropriate for analysis. So there's a lot of preparation and simplification involved in this red box here, before we can even get to the point where we're setting up the analysis, where we're applying loads and constraints and boundary conditions. We need to prep that geometry, and that can be a very time-consuming process. And then the meshing itself, once we've prepped our geometry so that it's appropriate for meshing, there's still work to do, even getting that converted to a mesh, which ultimately is what these products take as input for the analysis. When we're talking about the geometry input for a simulation, we're not really talking about a CAD model. Typically, we're talking about a mesh, and we use the CAD model to generate the mesh. And then we'll solve and we get to the results processing, which is ultimately our end goal. What what is the predicted performance of our product. SimSolid is going to get us to the same place. We're going to get to a point where we can set up an analysis and solve and get results, but we're going to be skipping these red boxes here. We're going to be skipping the CAD model prep simplification step and the meshing step altogether, which, as I said earlier, if you've done this at all, you know that that's typically the bulk of the time, at least the bulk of the time that somebody is actually sitting in front of the software and doing work. Sometimes analysis can take time too, but as far as the hands-on time that somebody is getting paid to do, much of it is getting that geometry ready and getting that mesh built. So by getting to the same place but skipping those steps, we are reducing the amount of time it takes us to get to that end goal. And of course, that means reducing the expense of the simulation, right? Because the time is money in more ways than one. The time for paying the analyst or the designer or the engineer to actually do this is a cost, but you're also thinking in terms of how long it takes you to get the answer. What does that cost you in time in terms of time to market, meeting deadlines or not? Right? These are all effects that that cost us money. So eliminating these huge steps is the biggest advantage of SimSolid. I've got a little video here that is not real time. I think it's about 22-minute event of a setup in a typical mesh-based FEA product where you know, you'll see that I've cut out some large portions of time. You could see the real time running at the bottom here. And what I really want to drive home is the length of time it takes us to even get to the point where it's meshing, and then what you'll see is the difficulty that the system has in meshing. So this is Inventor Nastran running inside of Inventor. And I don't mean to pick on it specifically. It's very typical of any mesh-based FEA product. You'd see the same processes. Right now, we're bringing the model into the environment. We're assigning materials. You're going to see me doing the same thing in SimSolid. There's really no difference there. We'll be adding some constraints to the model and adding a gravity load. But we'll get to a point here in Nastran, and we're 14 minutes in, and we're just now applying boundary conditions. A lot of the time that's been consumed so far is even just importing the geometry because there's so many parts, and Inventor tries to make some assumptions for you to get you started on the analysis. What kind of mesh would be appropriate, what sizes would be appropriate for the mesh. So just that part alone slowed it down. And we finally get to this point here where we're setting up the model. Momentarily, you'll see we get to the point where things really get messy, and that's the meshing phase. We're going to attempt to throw a default mesh on here and just let Inventor Nastran do its thing, which sometimes can be successful on simpler models. But you'll see in this complex assembly here, we're already seeing failures. And that goes on for about 8 minutes before ultimately the system actually crashes to desktop and fails altogether. So you might say, well, especially if you've got any experience in this, hey Rob, that's kind of unfair. You wouldn't just try and throw a default mesh on an assembly like this and hope it was going to work. And that's true. I wouldn't normally. But the reason I show you that is because when I get to SimSolid and show you that, that's exactly what I'm going to do. I'm going to perform those same steps, only it's going to work because it's not going to attempt to mesh. So why would I normally, when looking at a model like this, say to myself, well, there's no way I'm just going to throw a mesh on here and go. There's a lot of work ahead of me. I'm an experienced guy with this stuff, and I know just by looking at it that I wouldn't have gotten away with that. And the reason for that is there's common problems that come up in CAD models that we've produced for documentation and manufacturing that are going to prevent it from meshing successfully in our analysis tool. One of those problems is interferences between parts, right? We try to avoid too many interferences even when we're just talking about design, but sometimes interferences that we can get away with when we're making drawings or programming CAM systems or something like that, are allowed and ignored. We move on. Things like fasteners that interfere with the nuts because they're actually modeled on their major and minor diameters, and they don't actually have threads, right? So they interfere, and that's acceptable for our drawings, and it's acceptable for our design, but it's not acceptable for most mesh-based analysis systems. Those interferences will cause problems when generating contacts and when generating mesh. So that stuff would have to be fixed. So when you're talking about a traditional mesh-based solution to that problem, you're talking about suppressing parts that are causing the interferences, or merging them together using tools like shrink wrap or derived parts or something like that to convert these two interfering bodies into one, or using tools that subtract one from the other so that they no longer interfere, or actually just changing the design and going in and changing parameters and changing dimensions so that these things no longer interfere. And that takes time. And usually that means having a model that's completely separate from your design model, because all these changes you're making are going to be affecting your drawings. And so now you have two models, two different lives, two different paths, and you're spending a lot of time. Other issues are just in general complex geometry, small details, curvature, things that are handy when we have them presented in drawings, can cause us problems when we try to mesh them. The part you're looking at here, for example, is a hinge assembly downloaded from McMaster Carr. Very convenient for the designer to be able to put that in their drawing already assembled without having to model it themselves and have something to represent that. But it's causing a problem when we're talking about meshing all those fine little details, those little faces, that curvature, and this assembly here really adds no structural value. There's no point in having it in there. It doesn't have an um, a an impact on the results that's worth keeping it in there. But it may be necessary to connect two parts together, right? I can't just take it out altogether because now I have a gap in between two parts. That does affect the simulation. So I'd have to replace it with a simplified version of itself, find a way to fill in the voids here, remove these features. And CAD systems have come a long way as far as their tools for simplification and helping me to do that kind of thing, but it's still time consuming. And decisions have to be made, and it's work that really has no value. So that's typically what you're going to be doing in a mesh-based solution, is removing it or replacing it with a simplified version of itself. In SimSolid, the solution is just to leave it, right? And the same thing with the interferences. The SimSolid solution is just to leave it alone. SimSolid is very tolerant of interferences. It's gonna resolve the contacts, whether or not they're interfering, or even if there's small gaps. And in the case of these complex geometries, you could just leave them in. We're no longer meshing it. It's not a concern anymore. So to be fair to Inventor Nastran, yeah, I can get it to mesh, and I did in the case of this particular model. And a lot of the prep work that was required was applying those mesh-based solutions I just discussed. I had to suppress all the fasteners. I had to merge some parts. I had to replace some parts with simplified versions of themselves. And then I had to start going into mesh settings, even changing defaults so that the elements were small enough to even properly mesh these parts, because the system just didn't make the right assumptions about what element size would be appropriate based on the overall bounding box of the model. So I was able to get it to mesh successfully eventually, but I end up with a very large mesh, 6 million elements, and that 6 million element mesh is still too coarse. If you have any experience with meshing, you'd recognize that yourself. You could see things like very thin-walled bars here on my grating. Even though I've successfully got a mesh there, there's really only one element across the thickness of that. Same thing with like the thickness of the tubing that represents some of the bars, the handles, and things like that on this platform. That 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 element size is still too coarse, and it's going to result in an overly stiff model. It's not going to behave realistically unless I go even smaller and get at least 3, 4, 5 elements across the thickness of those materials, which is going to drastically increase that element count. It's going to drastically increase the hardware requirements to run it and the length of time to run it. So yeah, we could get it meshed with these tetrahedral elements, but there's work to even get there, and it's going to be very expensive to run. Eventually, I did try on this model using the tetrahedral mesh to get a good a mesh that I thought would be good enough to get good results, and I did run up against some limitations where the system was basically telling me you have too many nodes. I'm not going to do this. So the truth is, when I look at a model like this, I wouldn't have even attempted to mesh it with these tetrahedral elements. There are more appropriate element types to do this kind of thing. Things like, plates and line-based elements like bars, where we can replace standard cross-section structural elements for like frame members with lines, and analytically they behave correctly, but geometrically they're very simple. Same thing with the thin walls, sheet metal, vessel walls, things of that nature. We can use plate elements that have no geometric thickness, very low detail, but they behave analytically as though they had that thickness in them. So these techniques can help you, but this again is a lot of upfront work. Now, I'm a geek. I actually kind of enjoy doing this kind of stuff. I'm fine sitting here for 6, 8 hours building this little model and getting it to work right. That's just my nature. But I can tell you who doesn't like it, and that's anybody who is waiting for my answer or anybody who is paying for my time, right? My boss doesn't like it. My client doesn't like it. They would rather me not spend hours and hours converting that 3D model into a brand new model just to get it to run. So these techniques are there, they're available, they're fairly common in mesh-based systems today because of all the problems we just discussed that come up with CAD models. And that's another complaint you'll hear from your boss and your client. Well, we already have a 3D CAD model. Why are we modeling it again? Right? We already spent money getting it that far. Can't we just use that for the analysis? And that's a very valid question. And the answer should be yes. A lot of times it's no. A lot of times you're remodeling or you're spending a lot of time simplifying that model just to get it to work in an analysis. And that's the biggest advantage that SimSolid offers, is that this stuff goes away. We are going to use the CAD model that we already built for our design and documentation. We're not going to spend all this time prepping it or completely remodeling it just to get it to work. Because this stuff is hard, right? Even if you're going to use these techniques, these fancy elements that are better at representing these certain types of geometry, they come with their own problems. They connect together in weird ways. There's rules that govern how a line element can connect to a solid element, for example. You can't just connect them. They're not going to behave correctly. There's no stiffness at the connection. It's going to be like a universal joint. So you got to put this rigid connector on there. There are tools in a lot of these systems to convert your 3D models into plate elements by mid-plane meshing them. And if you've ever tried that, it's a handy way to generate the geometry, but it creates its own problems. Now you have gaps in between the parts where you didn't have them before, and you have to manually connect them. This is all stuff that it takes years to get comfortable with and learn how to do, and still takes time even when you do know how to do it. So I'd like to show you a better way. So what I've got open here now is the SimSolid interface. And what I'm going to do is start a new model, that same model that we've been looking at, that platform, and show you what it takes to get to results. So we've imported the geometry, and I'm going to allow the automatic connections to generate. So it's going to look at the assembly and create for me areas where the parts make contact. It's all stuff you can do manually or override. But right now, and this is pretty common too in any system, to have context generated automatically. That's nothing special, but SimSolid does it well. All right, so our contacts are generated. I'm going to assign some materials. Again, nothing too fancy about that. I'm just going to throw default steel on all my parts just to get this done quick. What we're going to do is just set up a very simple analysis, a static structural analysis under gravity load. Just a toolbar I gotta hide here. All right. So all I'm gonna do is create some immovable constraints, basically fixed constraints on a few surfaces here. We'll apply that, and I'll just throw some gravity on, and we'll go 1G and the negative Z. And we're ready to run. So this is where you're going to see the difference, right? This is where you're going to see the advantage. When did I not assign materials? Oh, I must have missed that. 1 second. There we go. Look at my assembly. All the parts have material assigned. Now I should be good. So no meshing. The solve has already begun. You're going to see it. It's going to happen very quickly. It's going to take seconds. No simplification. That model I brought in has all the interferences I showed you on the slides. Has all the complex geometry. I haven't simplified this at all. So I've been demoing simulation products for many years, and one of the primary rules is don't solve live, right? And the reason for that is it takes time, it wastes time. So usually you'd have some pre-baked results that you would then transition to after you've set up the model and get to the point where you hit go. Well, I don't have to do that here. It's already done. I just hit solve, seconds later, it's done. No simplification, just imported it. I got the contacts done, assigned the materials, and the materials could have been done for me too if I had a launch from a product using an add-in and there were material properties. I could have skipped that step too. But the important part is no mesh, quick solve, complex geometry, but we've already got results. We're just looking at displacement, exaggerated as usual, animating. So you may notice, if you've got a keen eye, that I've missed something here, and that was intentional. That little gap was made big enough so that we intentionally have something to fix there. Because I'd like to show you some other stuff like the ability to weld parts together, for example. So let's do that. I'll stop my animation. We'll go back to the setup. I know I had a little. See, the gap is big enough there that my automatic context didn't catch it. I could have with a larger setting in the automatic context caught that, but that wasn't my point. I just want to show you some other stuff while we're in here real quick, like the ability to weld parts together. So I'll pick a primary part here and then designate some secondary parts and find the welds. You can see a preview there. We've got the ability to control section size, assign materials to the weld, and we'll generate that connection where we didn't have one before. Not only that, but after I run, you'll be able to see results in those welds. Some other stuff to point out real quick is just things like the the bolted connections. I mentioned I didn't suppress any fasteners, right? And the reason for that is number one, I didn't need to, right? Even though there are interferences there and there's lots of, tiny little features on the geometry that normally would be a nightmare for me, these little chamfers and things like that, no longer a concern, but it also detects that these are bolted connections based on the shape of that geometry. And I get some very specific results as a result of that. I can see the internal forces on the bolt and the reactions on the connection when I run. So let's go ahead and run again. You can even add some torque on there. You could pre-tension those connections, which I haven't done in this case. So another advantage to being able to solve very quickly, right, is the ability to iterate. This tool is intended to be something that you use throughout the process, not something you just throw in at the end to validate your design, but use it as a tool to help you make decisions about the design throughout the process. And if you're going to do that, it means it has to run fast. You have to be able to iterate quickly. So I should have fixed my loose bars there. We could take a look at stress real quick too while we're at it. Let's see where our max stress is. So those results I was talking about, for example, we want to look at the resultant forces on the bolted connections. Everywhere that it detected those bolted connections based on leaving that hardware in there, I now have results at each one of these connections, right? I could zoom in on that. I could see the axial forces, shear forces, bending moment, etc. at that connection. Same with the welds. I can get my seam weld reactions, select the weld I'm interested in, and evaluate it. All right, here's the resultant forces on the weld, min max along the path of the weld, contact forces, stresses. And yeah, that's really what I wanted to show you is most importantly that I brought this complex geometry in. Here we could look at it in Inventor if you want. It's exactly like this. All these complex little parts, thin walls, tiny little features. That ugly hinge that I showed you, the cross section of, is still in there. All this stuff got launched exactly as is, and I didn't have to simplify or mesh. So if you're like me and you've been using these tools for a while, you might be thinking, too good to be true. I remember hearing about SimSolid years ago when it first came out before I had a chance to get hands-on myself, and I was thinking, yeah, that sounds great. That's a problem that needs solving and has needed solving for a long time. I'll believe it when I see it. I'm with you there if that's what you're thinking. And of course the best way to get rid of that head trash, as we call it, is to get hands-on with it and start solving some models yourself. But there is also plenty of resources out there for the validation and verification that all these products go through. For example, the organization NAFEMS is a internationally recognized a nonprofit that is dedicated to promoting and educating the world about simulation technology. And one of the things that they do is put out verification manuals that are standard problems that are solved by hand in a lot of cases, in most cases, and then solved in simulation as well. So these same standard models just get applied to any product and provide provide users, companies with a way of verifying that the product they're investing in can be trusted to give realistic answers. And every product you've ever heard of is has been applied in these manuals, and SimSolid is no different. So yeah, it works. If you ask me how they get to this point without meshing, it's still magic to me. I'm starting to get a handle on it, but it's really quite revolutionary. And maybe some of you out there could understand the white papers that they've published better than me. I'm slowly getting there myself, but for now, it's enough for me to see it in action and to see the problems being solved and the verification models. So it's still amazes me. So I hope it amazes you. If you've been using anything else, you're probably impressed. If you're new to simulation in general and maybe don't have have any experience in the problems that are being solved here by SimSolid, good for you. Avoid them and embrace the future of simulation. Don't get stuck learning the problems of the past. So with that, I will open up the floor for any Q&A or anything that's come through in the chat, or anything else that you would want to say, Evan. Pretty quiet, huh? Okay. Let's see here. Let me make sure this slide is unhidden. Edmund, I believe you wanted to talk about this, yeah?
Yeah. So in closing, before I actually get to that, but Robert, you can
Okay.
go ahead and leave that on there.
All right.
Just want to let you guys know that we're here. If you saw anything in the webinar that piques your interest, maybe some of the initiatives that you're currently working on, some of the challenges that you're facing, we'd love to meet with you. And so once again, if anything piqued your interest, please reach out to us. If you look in the chat, I did put my contact information on there. I have Robert, which is a technical expert on the Team D3 side. I also have an entire team at Altair that is supporting us in this. And so if you need anything, please reach out, let us know. We'd love to schedule some time with you to have kind of a discovery call, kind of find out what your initiatives are and challenges. And then from that point on, we can get a technical expert on there to really, really dive into all the details. So once again, make sure that you jot down my information and go from there. And I do see one question, but before we get into that, I'll go into the slide that Robert's got up. We are excited to be bringing back a virtual event that's coming up May 15th. So it's coming up really soon. It's called the ATCX Simulate at the Speed of Design. This is really geared towards small and mid-sized businesses. So if you're just starting to explore simulation, or let's say you're running into some challenges with speed or accuracy, or maybe you're thinking about diving into like multi-physics analysis, different things like that, we'd love to invite you to this virtual event, May 15th, 2025. And as we get into that last question, I am going to copy the link to the ATCX event. And so please steal that from the chat and join us on May 15th.
Yeah, so I see this question. Can you elaborate at all on how it does not need an elemental mesh? Yeah, I think I touched on that, how it's still kind of magic to me too. We can definitely follow up and get you access to the same white papers I'm currently still working my way through to trying to gain an understanding. They're super geeky, and you really kind of have to have a solid background in the theory behind these techniques to even begin to grasp it. It's all available. So we'd be happy to get that to you. I guess if I could summarize my understanding at this point, they've really found a way to apply the finite element method, but the elements can be of arbitrary volume and shape. So I guess I'm kind of thinking of the components of my assembly as the finite elements now. There's no more need to discretize them into standard shapes that we have formulas for. There's you can use any shape, and including the shape of your CAD model. There's obviously more to it, and I'm sure there's plenty that's still proprietary too, that may not be included in these white papers. But that's kind of what I'm grasping here, is that they've found a way to avoid having to use those standard element shapes.
All right, as we wrap things up, any other questions, anything that we can help you with? And once again, if you do have any questions, please type them up. In the meantime, please jot down my information, my contact information, and then also I added the link to the virtual event that's coming up May 15th. So please take that from the chat as well. If no other questions, we want to thank you for attending, and once again, just follow up with us if you'd like to schedule some one-on-one time. Thank you so much.
Thanks.